The thing that we have the chance to do is to repair those various things, to restore the structure and composition of the body at the microscopic level to something like how it was at an earlier age. So essentially repairing damage, doing preventative maintenance. And the idea there is that the body works perfectly well if it has a certain amount of this damage carrying around. It's just that there's a threshold level beyond which the body works less well. And that's why we get sick late in life. So this is really what it's about. It's not really stopping aging. It's doing periodic, comprehensive, preventative maintenance to essentially be a circuit breaker of aging.
Hi, this is Dr. Rosscarter with the Regenerative Warrior Show. Today, we're going to talk to Dr. Aubrey de Grey. Dr. Aubrey de Grey is a biomedical gerontologist. He's the Chief Scientific Officer for SENS Research Foundation, which is a nonprofit organization that is dedicated to funding aging research. He is also the editor-in-chief of Rejuvenation Research. I want to welcome our special guest, Dr. Aubrey de Grey.
Thank you for having me.
So you have been a pioneer in aging for a number of years. Actually, when I got started in regenerative medicine about 10 years ago, I saw a lot of your talks about aging, and that was totally fascinating to me. So you were definitely inspirational at that time. So your main area is really regarding how to stop aging. And I guess my first question is, how are we doing with that? How's that coming along?
Well, first of all, let me slightly be careful with the terminology, because so many of the words and phrases that people use in this space have been overloaded with connotations and so on. So I don't really like to say that the goal is to stop aging, because aging is a side effect of being alive. In other words, you get the accumulation of various types of molecular and cellular damage in the body as an intrinsic, inextricable consequence of the network of processes that the body has to do to keep us alive from one day to the next. The thing that we have the chance to do is to repair those various things, to restore the structure and composition of the body at the microscopic level to something like how it was at an earlier age. So essentially repairing damage, doing preventative maintenance. And the idea there is that the body works perfectly well if it has a certain amount of this damage carrying around. It's just that there's a threshold level beyond which the body works less well. And that's why we get sick late in life. So this is really what it's about. It's not really stopping aging. It's doing periodic, comprehensive, preventative maintenance to essentially be a circuit breaker of aging.
So yeah.
Now, coming back to the question, how's it going? Well,
yeah, how is it going? Are we actually accomplishing this goal, or are you?
So the best way to answer that is to start from the fact that any preventative maintenance approach to extend the longevity of any machine, even a simple machine like a car, beyond its warranty period, has to be a divide and conquer approach. It has to be a business of identifying all of the various types of damage that can eventually cause the machine to stop working and repairing them all. So you don't have to repair any of them perfectly because of what I said about this threshold, but you have to repair them all reasonably well. So how's that going? Well, not too bad. It's, the way that I've decided to essentially classify these types of damage is according to the ways in which we might go about doing the damage repair. And some of those ways are definitely further along than others. They were further along than others even at the beginning, 20 years ago, when I first conceived of this approach. But the good news is that they're all going pretty well. So the ones that were the hardest back then are still probably the hardest, the ones that have the most work to do, but they're a hell of a lot further ahead than they were. And things are accelerating as we get every incremental little bit of proof of concept, gets people a little bit more enthusiastic and confident that we might actually be able to do this. And so that means that there's more money available and things go faster as a result. So I'm pretty happy.
Do you think that the pandemic has actually hurt this cause or actually improved it somewhat?
It has hurt it. It hurt the cause somewhat over the past year, simply because there's been lockdowns that have meant people can't do as much work. There's been supply problems for various reagents, all that kind of thing. But I believe that it's going to be a huge benefit to this in the coming years, because it will concentrate minds on a whole bunch of things to do with the health of the elderly. First of all, from a political perspective, it's going to help policymakers, politicians, decision makers to understand that there are votes in actually doing something about the health of the elderly. Because you see, the elderly have this problem, they don't complain enough. If you say that you'd like to spend taxpayers' money, yeah, really. I mean, really, I'm serious. If you say you'd like to spend taxpayers' money on improving the health of the elderly, then the elderly will generally say, oh, no, you should prioritize health for the young because they've got more to gain. And the fact that this argument is completely circular is very hard to convey to people. But now, what we've got is the younger generation showing that the elderly matter to them. Because, of course, the younger generation are pretty much impervious to COVID, and yet they have more or less willingly submitted to this amazingly onerous limitation on their way of life, right? So that's very important. But actually, even more important is the economic aspect. The fact that the pandemic has obviously been unbelievably expensive, and just a little bit more youthful immune systems in the elderly would have just completely obliterated that, right? You would just have not had this. So yeah, there's a lot of bang for the buck there. Now, one big thing that we have to also take into account here is the progress that's already been made. Because you see, people have been trying to say, there's a longevity dividend. That's the phrase they use. People have been trying to say this for 20 years, that there is enormous economic benefit in just even slightly postponing the health problems of late life, right? Which is certainly true. But what those people have not been able to convince policymakers of until now is the idea that if money were given to researchers, then there would actually be any progress in postponing the ill health of late life. Basically, if you're a politician and you've got this idea in your head that aging is not like diseases at all and it's inevitable and universal and natural, then you kind of have the feeling that it's off limits to medicine, right? Right. Which means that this money that would be given to researchers to do this research would not actually deliver any postponement of aging at all. And therefore, it would be money down the drain, irrespective of how much economic benefit there would be if you had this success. The probability is zero of having success, and any number times zero is still zero. So that's why the argument has never succeeded in making any difference to public policy. Now, it's no longer scientifically valid, justifiable at all to say that the probability is zero, because the amount of progress that's already been made in the clinic, not even in laboratories, is sufficient to show that further progress would be greatly accelerated with better funding.
So what procedures would you say that are currently available to us are really making a difference with this I don't even want to say call it the aging process, but to help the age-related diseases? What current procedures are available to us?
Well, procedures is probably not quite the right word. So there are technologies that are making it easier to apply therapy. So, for example, we're just getting better at manipulating stem cells. When you inject stem cells into the body, they'd better be the right kind of stem cell, or they won't do any good and they might do harm. And that means that we have to be able to manipulate cells in the laboratory before injecting them so that they are the right kind of stem cell that we want. And there's been huge progress in the past decade in allowing us to do that. Then there's gene therapy, of course, modifying the genes of people that are already alive, modifying the genes inside cells. That has seen enormous breakthroughs. The best known, of course, is CRISPR, which was only developed less than a decade ago. And, improvements are being made to the versatility of CRISPR-like technologies every week. Mm-hmm. So those are improving things enormously. even with the immune system, vaccinations and such like have been around for 150 years, but the progress that's been made in the past decade or so in terms of essentially supercharging the immune system and making it better at doing what we need it to do against cancers, for example. These things have seen absolute leaps and bounds in the past decade.
Yeah, even our current vaccine is what's called an exosome, basically a messenger RNA surrounded by a protective coating, which is exosomes, which are how cells communicate. Hi, thanks for watching. Did you know that as we get older, we start to suffer from joint and spine pain and degeneration, chronic disease, and even accelerated aging, all caused by hidden weaknesses in our health? You see, daily metabolism leads to minor damage, and when that damage isn't repaired, then it accumulates until it reaches a threshold, and a health problem is created. Now, what if you could prevent these health problems from occurring in the first place? Now, science may have finally found a way to stop this process through cellular preventative maintenance. Regenerative nanoparticles are a revolutionary solution that can find and repair hidden damage before it becomes a condition. Discover how regenerative nanoparticles can add 30 or more healthy years to your life. Simply go to drrosscarter.com and set up a time to chat and learn more. That's drrosscarter.com. Now, we're located here in South Florida, but these procedures are available in all parts of the country. Please note that these procedures are not covered by insurances and prices start at $2,500. Go to drrosscarter.com and I will talk to you soon. Take care.
So there's two parts to that, actually. So yes, exosomes are one way in which cells communicate with each other. And again, this is a whole area that's very new. 10, 15 years ago, hardly any biologist had heard of exosomes. In fact, they probably, there's a long way to go.
Still haven't.
There's a long way to go in terms of understanding how we can manipulate exosomes therapeutically. But the mRNA component is also interesting. So the idea of having an mRNA vaccine is itself pretty new. And these things are much more versatile. In particular, what we're seeing right now is with these new variants of COVID that are coming up, mRNA vaccines are particularly easy to modify to essentially match the spontaneous mutations that are occurring that are causing these variants to emerge and to progress. So yeah, great progress.
Yeah, I'm excited about that. How about your? Well, I'm curious about you. I mean, are you taking steps now to be able to continue your work for your late 50s, right? What our life expectancy is around 80 years old. What are you doing right now? What steps are you taking for yourself to be able to preserve yourself so that you can last longer? Yeah.
So I'm a lucky guy. I seem to be well built. So I've had my biological age measured in various different ways half a dozen times over the past 20 years, and I always come out ridiculously much younger than I really am. So that's great news, of course, and it means that I have to be very conservative. I have to take the rational thing for me to do is to be, if it ain't broke, don't fix it, right?
Right.
But at the same time, of course, I'm also always paying close attention to progress that's being made, because there will come a point where the risk-benefit ratio is positive for me to actually partake of such things. At the moment, though, I'm not doing anything except, of course, spending all my time trying to accelerate this research.
So I was looking at your categories, and one of them was talking about the cancer cells, basically, where they have the ability to really last forever, and that's a very weird concept for me. So can you explain to me something that I don't understand? Why is it that cells have these telomeres where they'll self-destruct, but when they malfunction, they turn into like a superhero, and then they can continuously live forever and ever? How did they figure that out? And because one of the cardinal signs that I've seen on other lists talks about the shortening of telomeres causing problems with aging, whereas yours talks about because of that on cancer cells, that also causes aging. So I'm confused about those two concepts.
Right, yes. So the whole business of telomere maintenance is, as you say, a very, very double-edged sword when it comes to aging. There are aspects of aging that are driven by telomere lengthening, namely cancer, and there are aspects of aging that may, to some extent, be driven by telomere shortening. So we have to find a way to get the best of both worlds, and it's not easy at all. So most of the effort that's gone into telomere manipulation in relation to aging has been on the side of extending telomeres so as to make cells more able to divide. And everyone recognizes that this may have a bad side effect in terms of increasing one's propensity to dying of cancer. But it turns out that even that is really complicated to tease apart for two reasons. First of all, you can't really do experiments in small model organisms like mice because they have completely different telomere biology. And secondly, because the impact on cancer is itself not a simple one in humans. It may be that actually extending telomeres slows down the accumulation of other mutations in precancerous cells. Because a cancer, in order for a cell to become cancerous, it has to mutate a bunch of stuff, right? It has to be able to evade a whole bunch of machinery that the body has to stop it from dividing uncontrollably. So it may actually, that may actually help. But this one extra last thing, this business of turning telomerase on, this enzyme that extends telomeres, that may outweigh that. Because you see, the thing is, it's far, far more difficult to turn a gene on by random mutation than it is to turn it off by random mutation, right? Turning a gene off by random mutation is just, you break it. You just have anything that goes wrong, anything. But turning it on, you have to have a bunch of different little subtle things that happen in the region nearby the gene and so on. And indeed, people a long time ago asked the question, they said, okay, in what order do mutations happen in cancers? And they found that telomerase activation tends to happen last, which indicates that it's the hardest thing to happen, right? Mm-hmm. So it may be that if you stimulate telomerase and thereby extend telomeres, then cells are less likely to accumulate all the other mutations they need. But because they don't have to have this last mutation to turn telomerase on because you already did it, they actually become fully cancerous more easily because that kind of the probability multiplies up. And we don't know the answer to that. We just don't know yet, right? So, yeah, but we have a kind of indirect answer, and I rather like indirect answers. Biologists are not very good at this, in my considered opinion, and I think this is something that I'm perhaps different from most biologists by virtue of my original mathematical and computer background. That I notice easily when there is an indirect argument that, despite being indirect, is a really strong one, and in particular in this case. One thing we have to notice is that all large mammals have adopted this same policy of suppressing the telomerase gene, so that they have the bare minimum of telomerase expression that in any given cell type that they can afford to have, which in most cell types is exactly zero, and in other cell types, like the stem cells of the blood, for example, is almost zero, but not quite. So that nobody has thought of any explanation for that, any evolutionary explanation, other than the idea that it protects us against cancer, right?
Right.
So yeah, this is where we're coming from. So this is why I say, in order to get the best of both worlds, we should probably be looking at using telomerase suppression and telomere shortening as an anti-cancer mechanism, and just somehow coping with the side effects that we have on stem cells and so on. In some other way, like putting new stem cells in, for example, rather than going in the opposite direction and
augmenting all the telomeres.
Right.
Huh. That's interesting. Okay. Now, in regards to in regards to therapies and treatments available in the United States, when you were talking about stem cells, we don't really have the ability to utilize, in a clinical sense, expanded stem cells. Are you using allogeneic or autologous?
Okay, so first of all, we at Sense Research Foundation don't do any stem cell work to speak of.
Okay.
We But also you have to remember that the whole question you're asking doesn't arise when you're doing stem cell research in mice.
Right.
Right.
You do whatever you want.
And that's what we do. We don't do clinical trials. We do early stage stuff. So really your question is not about what Sense Research Foundation does. It's about what the community is doing in this regard.
Yes.
And there, well, the trade-off between allogeneic versus autologous is the same trade-off that it's always been. Allogeneic cells will be subject to immune rejection, whereas autologous cells are really expensive and difficult and laborious to make. So that trade-off hasn't changed. There are some things that are improving, of course. The fact that we can make autologous cells from iPS cells now. A company that I was involved with for a couple of years called Ajax Therapeutics has a really cool way to create lineage-committed adult stem cells from iPS cells with much higher purity than what was possible in the past. That's really important, of course, because you really don't want to inject. And if you take a population of iPS cells and you differentiate them, into neurons, into neuronal precursor cells, for example, you're going to have some iPS cells left. You're going to have some pluripotent cells that are still pluripotent, and that's bad. So, so we're making, there's various little bits of progress here and there, but the ultimate trade-off remains the same as it ever was.
Understood. Yeah. And regarding how about senescent cells, how have we progressed with the elimination of these type of cells in our body?
Quite a lot, really, really rather a lot. I mean, 20 years ago when I first developed the sense classification, my view was that the only plausible way to get rid of senescent cells was genetic, that we would have to identify identify various genes that were being overexpressed in senescent cells and use suicide gene therapy to get rid of those cells. Which is a technique that's been, standard in the laboratory for a long time, but it's very tricky to do in the clinic. Of course, that is still being pursued by some companies in this space, but the real revelation, which surprised the hell out of me, is that it's been possible to develop drugs, small molecules, that can selectively kill senescent cells. Well, selectively enough, anyway. And that's why we have this proliferation of companies that are doing very well in that regard, some of which are already in clinical trials. So I'm really impressed at how that's going. The third approach to killing senescent cells, which is also really exciting, and we are doing a bit of work on this at Sense, is to stimulate the immune system. So just as we have cancer immunotherapy, we can have senescent cell immunotherapy to identify cell surface markers that are selective, reasonably diagnostic of being a senescent cell, and get the immune system to pay attention to those markers. In fact, various people have been, it's become quite popular to say that senescent cells are actually cancer cells that are not dividing, which is, maybe not a terribly useful thing to say, but some people are saying it.
Hi, thanks for watching. Did you know that as we get older, we start to suffer from joint and spine pain and degeneration, chronic disease, and even accelerated aging, all caused by hidden weaknesses in our health? You see, daily metabolism leads to minor damage, and when that damage isn't repaired, then it accumulates until it reaches a threshold, and a health problem is created. Now, what if you could prevent these health problems from occurring in the first place? Now, science may have finally found a way to stop this process through cellular preventative maintenance. Regenerative nanoparticles are a revolutionary solution that can find and repair hidden damage before it becomes a condition. Discover how regenerative nanoparticles can add 30 or more healthy years to your life. Simply go to drrosscarter.com and set up a time to chat and learn more. That's drrosscarter.com. Now, we're located here in South Florida, but these procedures are available in all parts of the country. Please note that these procedures are not covered by insurances and prices start at $2,500. Go to drrosscarter.com and I will talk to you soon. Take care. It could make sense. I mean, it never figured out how to improve their telomere length, so they couldn't divide. What about supplementation? Have you seen any type of natural type of therapies or supplements that could actually minimize or get rid of some of the senescent cells?
Well, there are some reports that some things do this. So ficitin is a particularly
Yeah, that's the one I'm thinking of.
popular one right now.
Yeah.
But I think at this point, the smart money says that artificial pharmaceuticals are likely to do better in the long run. However, we still don't know whether they're going to be good enough, or whether these other approaches, like immune stimulation against senescent cells, are going to be better still. There's still a lot of work going on, and I'm happy that it's very diverse right now, because we're never going to know until we try.
Yeah, I know there was a company, Cellularity was expanding NK cells, and they were using those against COVID. Is that something we could use against really any senescent cell, or to enhance anybody's immune system?
So yeah, so absolutely. So we are actually looking at this ourselves. We've actually been in communication with Cellularity about this. And yeah, NK cells are looking pretty promising as one of the ways to go anyway.
Yeah, I was excited about that. Now, one of the cardinal signs that I was looking at was DNA damage. Now, on your list, I didn't see anything that indicated damage to the DNA.
Right.
So, but that's kind of one of their primaries that cause a lot of problems. Where would that be on your list, and why would you not add it?
Okay, so first of all, remember that there's one type of DNA damage that is very much on my list, which is mitochondrial DNA damage.
Mitochondrial, yeah, because they have their own.
Right. But if we go to the nucleus, then you're absolutely right. It's not there. It's kind of there, though, because I've got cancer. And of course, cancer is caused by DNA damage. And indeed, senescent cells are caused by DNA damage. But that's all I've got. You're quite right that it seems rather conspicuous that I do not have general DNA damage in there. So why do I not? The answer is a concept that I came up with maybe 15 years ago called, well, more than that actually, called protagonistic pleiotropy. So what the hell is that? Okay, so it's kind of a play on words, because about 60 years ago, 70 years ago almost, there was an idea put forward called antagonistic pleiotropy, which was essentially an explanation for why we have genes that appear to be bad for us late in life. But without going into too much detail, essentially what I ended up reasoning was that cancer is the phenomenon that really drives the evolution of DNA repair and maintenance machinery that we have naturally. The quality of that DNA repair maintenance machinery needs to be sufficient to stop us from dying of cancer before we have had kids, or else, there's no next generation, right? And the same machinery is used across the whole genome to maintain all the genes that we have that don't have anything to do with the cell cycle, right? Mm-hmm. Now that means that if you look at the consequences for health, then they're not the same, right? Cancer can kill us just with one cell getting the wrong constellation of mutations, right?
Yes.
But for anything else to be bad for us, it has to affect a lot of cells, like a substantial proportion of the cells in a given tissue. In the same way, they have to all stop being able to do such and such a thing, like oxidative phosphorylation or whatever. And that's a hell of a lot of cells, and that's just not going to happen. It's just a numbers game. It's not going to happen. So basically, what this means is that the requirement to avoid getting cancer before we've had kids has driven evolution to make our DNA repair and maintenance machinery unnecessarily good for everything else. So that means basically, we won't see any health consequences of of DNA damage other than cancer until we are many, many times older than we can be naturally. So that's why it's not on my list.
Because it's not something that happens normally first, right? Is that what you're saying?
Right.
Okay. Now, what about intracellular or altered communication, the communication issue?
All right. So this is you're highlighting a hallmark of aging, as they were called in 2013 in that famous paper in Cell.
Yeah.
It again, looks as though it's missing from my list. There's a very good reason why it's missing. And this is because what they're talking about there essentially is what changes in the bloodstream, in the circulation. That's what it's all about. It's all about, old blood is somehow more contaminated or less high quality than young blood. And that's why these very interesting heterochronic parabiosis experiments are so exciting. Why, if you take a young rat and an old rat and you join their social systems together, then the old rat enjoys it. Right. So why is it not in my list? Simple. Because what's in the blood is determined by the activity of cells. Cells of different organs are, secreting stuff into the blood, and they're taking stuff out of the blood. And some of the stuff that they secrete is good and some of it's bad. Some of the stuff they take out is good and some of it's bad. So basically this means that if you fix the cells, then the bloodstream is going to come right on its own. So in other words, the circulation, yes, I mean, we can have kind of, stopgap quick fixes that involve rejuvenating the blood. And I'm all in favor of stopgap quick fixes so that more people can get to longevity escape velocity, but it's not a fundamental thing. Ultimately it's an epiphenomenon of the other things.
Understood. Yeah. And what about, now you talk about the garbage in the cell as well as garbage out of the cell, which I didn't actually notice was a part of the other list, but I thought it had to do with nutrient sensing. I don't know if it's not the same.
Not at all, no. So the hallmark from the 2013 paper that is most analogous to my intracellular and extracellular garbage is loss of proteostasis.
Oh, right. Okay, the protein misfolding. Hi, thanks for watching. Did you know that as we get older, we start to suffer from joint and spine pain and degeneration, chronic disease, and even accelerated aging, all caused by hidden weaknesses in our health? You see, daily metabolism leads to minor damage, and when that damage isn't repaired, then it accumulates until it reaches a threshold, and a health problem is created. Now, what if you could prevent these health problems from occurring in the first place? Now, science may have finally found a way to stop this process through cellular preventative maintenance. Regenerative nanoparticles are a revolutionary solution that can find and repair hidden damage before it becomes a condition. Discover how regenerative nanoparticles can add 30 or more healthy years to your life. Simply go to drrosscarter.com and set up a time to chat and learn more. That's drrosscarter.com. Now, we're located here in South Florida, but these procedures are available in all parts of the country. Please note that these procedures are not covered by insurances and prices start at $2,500. Go to drrosscarter.com and I will talk to you soon. Take care.
In particular, the accumulation of misfolded proteins. So there's a couple of things that distinguish my classification from their classification in this regard. The first one is they're not distinguishing inside the cell versus outside the cell, okay? And the second thing is they're only talking about proteins. They're not talking about garbage that's not made of proteins.
Right. All the other stuff.
Right. So my two categories of garbage in combination are actually a superset of their category, right?
Right. Okay.
And this really highlights the reason why their classification and mine are different. Their classification is more driven by what's fashionable and how biologists intuitively partition things.
Yes.
In terms of the types of damage, whereas my classification is driven by what we can do about it. In other words, what types of repair therapy seem to be plausible to develop. So, number one, we have to ask, why have inside and outside the cell be different? And the answer to that is that we have different pre-existing natural machinery inside and outside the cell for breaking garbage down. Inside the cell, you've got the lysosome, which is this crazily versatile machine, this incinerator with dozens and dozens of enzymes that break almost anything down. Not quite everything, but almost anything. Outside the cell, you haven't got that. You've got a far more primitive, less versatile machinery. So that means that nearly everything that accumulates outside the cell, simply the only reason it accumulates is because it's not got access to the lysosome. And if it could only become inside the cell, if it could only be sucked in and swallowed, then it would be toast very quickly. And that's exactly what has already worked. So way back, actually, one of the inspirations for my whole classification back in 2000 was the work published the previous year, showing that in mice that have been modified so that they get Alzheimer's disease, in particular so that they get amyloid accumulation, which is, of course, outside the cell, all you needed to do was vaccinate, was use the immune system to get the immune system of the brain, the microglia, to engulf this stuff, and it would go away. because inside the cell, the machinery inside the lysosome is perfectly competent to break down amyloid. And of course, that went through the clinical trial process pretty quickly because Alzheimer's is a very big deal, and it works. You've now got, I think, 4 different different immunization protocols that have gone and succeeded in phase 3 clinical trials in demonstrably removing amyloid. Of course, you can see amyloid in PET scans now. You don't need to kill people. You can do it non-invasively, right?
That's good. Good news.
Right. So that works. Of course, in terms of actual clinical cognitive benefit, it does basically nothing. But that's no surprise at all, because Alzheimer's is a very multifaceted thing. It's got lots of different types of damage, just like aging itself, right? So I wasn't at all surprised to see negligible cognitive benefit, but we've got this one thing in our back pocket now. And the good news is that, of course, there are other things that go wrong in other types of amyloid that accumulate in other tissues late in life, where the amyloid is definitely causative. And if you can get rid of it, then you're probably going to have genuine functional benefit. And we've pursued that with a group in Texas, especially, to get rid of amyloid in the heart. And that's now turned into a startup company. So yeah, it's very good news. But you can't use immunization against stuff that's inside the cell, because first of all, the immune system doesn't really see what's inside the cell. And secondly, the stuff that's inside the cell, the lysosome should be doing everything, and you've got to do better. So what we do there is a completely different therapy. What we do is we find new enzymes that the body normally doesn't have. We find them in bacteria, and we find the genes for these enzymes, and we introduce them into cells, the incineration machinery that the lysosome has, and thereby allow it to break things down. So we did that. Our first 2 targets there, starting maybe 15 years ago, were actually neither of them was a protein. One of them was a derivative of cholesterol, which accumulates in the macrophages in the artery wall and is the main driver of atherosclerosis.
That's what I was going to ask you about as well. Yes.
And the other one was a derivative of vitamin A, which accumulates in the back of the eye and is the main driver of macular degeneration. And in both cases, it worked. We found enzymes that could do the job. We introduced them into cells, and we got better survival. And both of those things also ended up in spin-out companies. So yeah, this is definitely an approach. Now we've only just now started working on proteinaceous aggregates, on the things that the Hallmarks paper in 2013 talks about. The reason we waited was because, of course, proteins are far harder to distinguish, because we don't want to break down all proteins, right? No. These oxidized cholesterol derivatives, they are single small molecules that are very different from anything else that we don't want to break down, whereas proteins are pretty much the same as things we don't want to break down. So we've got to be very careful. And what we're going to be doing now is actually we are going to be using the immune system in a way. We've got a clever trick for getting antibodies into cells and causing those antibodies to break down these proteins. So that's what we're going to pursue. Of course, antibodies don't normally break things down. They normally just bind to them. But there's a special type of antibody that we've been working with that's actually proteolytic. It actually chops up its cognate antigen.
What is it called?
They're called catabodies. And so they're antibodies. Yeah, they're antibodies, but they are subtly different. So they actually have proteolytic activity.
Well, that is awesome. And yes, so you're using this to get into cells to phagocytize the garbage, basically. Is that what you're doing, or is it binding to it?
Well, not phagocytose, because phagocytosis, of course, is the process. No, we're not doing that. The stuff is already inside the cell, right? Right. So the antibody into the cell. So the antibody has access to the garbage, right? Like tangles, for example, in neurons, right? Yeah. And then the antibody attacks the garbage directly, and chops it up. It chops it up. Yeah.
Oh, okay.
Yeah. Now another thing that makes this plausible is in neurodegenerative diseases like Alzheimer's, this proteinaceous garbage, which is probably very important, does not get to the lysosome. What happens is that the lysosome is somehow inactivated, possibly by oxidized cholesterol, actually, and it stops internalizing stuff. So the aggregates, like the tangles, they stay in the cytosol, in the main body of the cell. And for our purposes, that's a really good thing, because the antibody needs to attack it. And
Yeah.
you don't want the antibody to get into the lysosome because the antibody itself will be broken down in no time at all.
Yeah. And so you're using this for brain treatments?
We're going to try and use it for the brain. That's right, to get rid of tangles. We're hoping that if you have a treatment that gets rid of tangles and also a treatment that we've already got that gets rid of plaques, remember I just mentioned, then then you might have a very substantial cognitive benefit.
And are you using that for the atherosclerosis as well?
Oh no, because in atherosclerosis you don't get proteinaceous aggregates inside cells.
Okay, what is? I remember reading about or listening to this, which is where the white blood cells are basically sticking to the walls, is because they're trying
Got it. So there's a particular type of white blood cell, the macrophage. Okay.
Yes.
So they go into the artery wall, and that's all perfectly normal and physiological and a good thing, because what they do in there is they engulf stuff. That's what macrophages do. Now, of course, macrophages sometimes engulf bacteria and so on. In this case, they engulf basically detritus, which is mostly cholesterol. It's like bits of LDL particles and so on. And they just get inside. Now, regular, normal, unoxidized cholesterol is not a problem here. The macrophage knows what to do with that. It processes it and it re-exports it and recycles it. Perfect, no problem at all. The problem comes because this garbage, this detritus, has this relatively low but non-zero concentration of contaminants in it, which are basically variants of cholesterol. In particular, there's one called 7-keto-cholesterol, which is really nasty. There's not much of it, but there's enough that the macrophage gets very upset and basically stops working. It stops being able to process normal cholesterol even. And that's the first stage of atherosclerosis. The macrophage becomes this thing called a foam cell, FOAM. And those foam cells accumulate and accumulate more, and eventually they get to, and they secrete inflammatory signals. They say, listen, I'm in trouble. Some more macrophages come in to try to solve that problem. And of course, those macrophages become part of the problem because they can't do anything either with this stuff. So that's how a plaque grows. And eventually the other cells, like the vascular smooth muscle cells, get angry as well, and it becomes a plaque.
Hi, thanks for watching. Did you know that as we get older, we start to suffer from joint and spine pain and degeneration, chronic disease, and even accelerated aging, all caused by hidden weaknesses in our health? You see, daily metabolism leads to minor damage, and when that damage isn't repaired, then it accumulates until it reaches a threshold, and a health problem is created. Now, what if you could prevent these health problems from occurring in the first place? Now, science may have finally found a way to stop this process through cellular preventative maintenance. Regenerative nanoparticles are a revolutionary solution that can find and repair hidden damage before it becomes a condition. Discover how regenerative nanoparticles can add 30 or more healthy years to your life. Simply go to drrosscarter.com and set up a time to chat and learn more. That's drrosscarter.com. Now, we're located here in South Florida, but these procedures are available in all parts of the country. Please note that these procedures are not covered by insurances and prices start at $2,500. Go to drrosscarter.com and I will talk to you soon. Take care. And so is there a solution that you're working on to help with this problem?
Oh, yes. So that's the solution that does not involve antibodies. That's the solution I mentioned earlier, where we find enzymes in bacteria that are not antibodies, but they are proteolytic. Now, in this case, we do want those enzymes to be in the lysosome because that's where the oxidized cholesterol gets to. And that's what we've done. And it works, in cell culture anyway. Actually, right now, however, we have another spin-out company called Underdog, which is working on an alternative to this, a very clever alternative. So if you think about it, the problem is the accumulation of this oxidized cholesterol in the macrophage. There's two ways to stop that accumulation from happening. One is to break it down, right? And the other is to excrete it, to get the oxidized cholesterol out of the macrophage and into the bloodstream in such a way that eventually it gets excreted out of the body through the kidneys. And we've got a way of doing that. Essentially, we're using a very well-known safe molecule called cyclodextrin. We've modified this molecule in a particular, clever, ingenious way so that it's rather good at encapsulating this oxidized cholesterol and dragging it out of the cell, sucking it out, and then excreting it. And so that's now looking very promising. Should be in clinical trials in a year or two.
That's exciting. That's a good one. What about the extracellular crosslinks? I was reading about that as well. As it's like the handcuff situation of the proteins. I haven't heard anything or you talk about that at all.
Yeah. So first of all, the hallmarks people just left it out completely. They just like they just forgotten about it. The day after the hallmarks paper came out, I wrote to all the authors and I said, "Hello, what about glycation?" And they wrote. One of them wrote back and said, "Oh dear, it's terribly embarrassing. We should have had 10 hallmarks." But anyway, yes, I haven't forgotten about it. So yeah. So what's going on there is that the various tissues become less elastic, stiffer, and even wrinkles. So there are cosmetic applications, of course. These things are all to do with loss of elasticity. And we understood the chemistry of this for decades. Basically, what happens is that sugar in the bloodstream reacts with proteins in the extracellular matrix, this lattice that gives this elasticity. And those reactions sometimes cause additional covalent bonds, chemical bonds between these proteins, which cause this stiffening. Now, the molecular structure of those new chemical bonds that we don't want turns out to be really weird and baroque, very different from anything that the body lays down on purpose, which is great, of course, because it means that we have a chance of identifying drugs that can selectively react with these unwanted bonds and break them again without having consequences elsewhere. But it turns out to be harder than that. However, we didn't give up. We funded a group at Yale University for several years to work on this, and they cracked it. They worked out how to do this, especially for one particular crosslink, which seems to be the most abundant one in humans. And that, again, is a spin-out company now. It's called Revol Pharmaceuticals. And it's, getting to the point of being able to actually break these things in people.
And when you're able to do that, what is the result that's going to happen because of that?
Well, we would expect that the tissues that have become less elastic will become more elastic again. So if you think about, for example, the major arteries, which is a big thing here, when the major arteries become stiffer, the heart has to pump harder in order to get blood to the rest of the system, because there's less, energy conservation in the stretching. And so we could end up with a very good permanent treatment for high blood pressure. Of course, we've got other treatments for high blood pressure already, but they kind of are nibbling away at the edges of it. You've still got this inexorable process going on right now at the foundation of all of this that's going to make those drugs work less and less well as people get older. So we need to actually address the root of the problem.
Excellent. Now, when I was listening to you speak before, you talked about your excitement in the area of making a major change that is really something that's almost available to us. Would be one thing is the maintenance portion of, where we have metabolism, then, we're trying to maintain it so that we don't get to the disease state, correct?
Yeah.
And you were talking about regenerative therapies there, and also the elimination of the non-functional cells. And the combination of those two would be kind of like a game changer for a lot of people. Is that accurate, or am I off?
Combining things. Well, I'm sure.
Yes.
I mean, we have to combine everything in the end, right? Now, actually, I predict that this is going to be an increasingly major theme of Sensory Research Foundation itself, because it is it's particularly unattractive for the private sector. In the private sector, you always want to make money quickly, and you've got to focus on something. So we've had great success in creating spin-out companies, both from Sense itself and also many companies that have arisen independently of us, addressing some individual type of damage repair. Okay, wonderful. But in order to combine these things, you've got to get all these things working individually, and then figure out whether there are any unforeseen interactions that you will need to get rid of. This is not attractive to a company typically, at least not at first, not until you've got a long way through the safety and everything. So we're already starting to do that. We have one project right now, which is in mice, just co-administering mesenchymal stem cells and one of the more popular senolytics to get rid of senescent cells. to see, whether we can get synergistic effects. And this is just the first step in, combining more and more of these things once each of them individually works.
You haven't done this yet, or this is what's upcoming?
We've just started that very first experiment quite recently.
And it has that combination. So you don't, I guess you don't have a prediction of what's going to happen with that, do you?
Oh, we don't predict the results of experiments. No.
I don't know. You just hope for the best. When will you actually have that or those results ready? I mean, how long does it take to find out?
Well, mice, obviously we don't want to use, short-lived mice that have some kind of problem of accelerated aging, because you can very easily be misled by them. So we have to use regular mice that live maybe 2.5 years. And we're hoping, obviously, to get them to live longer. And we've only just started, so it's maybe 2 years away. Of course, we will be doing a bunch of other stuff on these mice before they die, measuring functional stuff, and anything we can to determine their biological age throughout. But we don't know.
Fascinating. So your company is called Sense, SENS, and what does that stand for?
You really want to know? It stands for Strategy for Engineered Negligible Senescence. And that was, we don't talk about that very much. It basically came from, so the term negligible senescence was already established within the literature, within the biogerontology community when I came along. So it was kind of just working from that. But yes, and remember also, it's not a company. We are a non-profit, a 501c3. So anyone who wants to give us money will get a tax write-off. Our business model is, as I've alluded to occasionally already through the interview, to take projects to nurture projects for as long as it takes until they reach a certain level of proof of concept, and then to spin them out as startup companies that can go much faster because investors tend to write bigger checks than donors do. So that's our model. But yes, we're a non-profit, and we work on the things that are still not at the stage where people will view them as investable.
Got it. And then, so once you prove a concept, then you just move on to another concept. Is that kind of how the process works?
Kind of, yeah. I mean, of course, we're working on multiple different things at the same time at any point. But yeah, absolutely. We, so for example, the reason why we've only just started to do this combination experiment with stem cells and senolytic is because it didn't make sense to do it until we had particular treatments of those two things individually that were working quite well in terms of extending longevity in mice.
When you use a senolytic, is it something that has been used in humans that we know that'll be okay to utilize, or do we not know?
Well, of course, we have multiple goals here when we're doing mouse experiments. We want to get more information that will eventually be useful in the clinic, but we also want to, to have things that will work in mice just for the sake of getting them to work in mice to get people's confidence up. So yes, of course, we would tend to bias. We tend to work preferentially with interventions that could also eventually be used on humans, but we're willing to finesse that a bit depending on the circumstances. So, for example, some of the things that we're working on involve genetic manipulations, which would require somatic gene therapy in humans, and that's still a few years off from being really doable. I mean, maybe only a few years. People are already thinking about doing clinical trials with CRISPR and so on. And of course, in certain circumstances, like especially in the eye, which essentially gene therapy is much easier in the eye because there's basically no immune system. There are already plenty of clinical trials with gene therapy. So, we're willing to kind of rely on gene therapy catching up and get things working in mice, even if
beautiful. Excellent. Well, you've done wonderful. I'd like to hear the different information that I haven't heard from you before. And I know you say that you do the presentation a lot. So I appreciate you answering the questions, because those were the things I was really curious about. Okay. And I'm excited for the progress of your nonprofit organization. And anybody listening who is interested in making a donation, they would always welcome that, I'm sure. But it really goes towards the future of our health, and no one wants to grow old and get disease and die.
You're very yeah, I mean, just put our website in the show notes and in the notes of the thing, and yeah, there's a lot of information on our website written for every kind of audience, from absolute experts all the way through to complete novices, as well as, of course, there's a contact form. So any questions that you have, you can always ask, and we're very well behaved at replying to those. And yes, as you say, there is a nice friendly donate button as well.
There was. I did go to your site and did a lot of reading before we talked. So thank you for that. And I want to thank you so much, Aubrey, for coming on the show today. It was a pleasure to speak with you, and the information, it was invaluable. So I thank you so much for your time today.
It's my pleasure. Thank you for having me. Bye-bye.
Right. Hi, thanks for watching. Did you know that as we get older, we start to suffer from joint and spine pain and degeneration, chronic disease, and even accelerated aging, all caused by hidden weaknesses in our health? You see, daily metabolism leads to minor damage, and when that damage isn't repaired, then it accumulates until it reaches a threshold, and a health problem is created. Now, what if you could prevent these health problems from occurring in the first place? Now, science may have finally found a way to stop this process through cellular preventative maintenance. Regenerative nanoparticles are a revolutionary solution that can find and repair hidden damage before it becomes a condition. Discover how regenerative nanoparticles can add 30 or more healthy years to your life. Simply go to drrosscarter.com and set up a time to chat and learn more. That's drrosscarter.com. Now, we're located here in South Florida, but these procedures are available in all parts of the country. Please note that these procedures are not covered by insurances, and prices start at $2,500. Go to drrosscarter.com, and I will talk to you soon. Take care.